Welcome back. This is Professor Elliott once again, and this short video will go over some basic concepts in diode biasing. Okay, so in our last video we looked at basic semiconductor theory, a little bit about N and P-type doping and barrier potentials and all that good jazz. So anyway, in this video, look at some more practical stuff, I guess. So here we have a basic, very simple diode circuit, and we have a 12-volt battery. We have a standard silicon diode. Okay, note the barrier potential. This is the standard symbol for a diode. This is the anode, and this is the cathode. Okay, so notice the symbol. Okay, and here we have a load resistor RL. Because the anode, this is the side here, is going to the going to the positive source. So this is like the positive side of the diode, right? We know this diode is going to be forward biased, and the flow of current, if you use conventional flow, is going to be positive to negative like this. Okay. Now normally throughout the course I use conventional flow. Here I've shown you electron flow because that's the way it really is. Okay. Don't really care how you think of it. Electron flow is how it is. Conventional flow is the way it's been traditionally taught at Mohawk College. So I normally haven't deviated from that. Anyway, so you can see here I have a simple current calculation. So with the diode being what we call forward biased, this is acting like a closed switch. It's a good memory aid. Okay, not exactly equivalent, but it's good enough. Anyway, so we have current, if we use conventional flow like this, right, or electron flow that way. So we have 12 volts here. We have 0.7 volt barrier potential here. That gives us 11.3 volts, 1 k ohm. Ohm's law says we have 11.3 milliamps. Okay, this is just a little reminder note about the depletion region. We talked about that last time. Okay, so this is current in a forward biased diode. Okay, this is current in a reverse biased diode. When the diode is reverse biased, okay, as a memory aid, you may think of it as an open switch. It's not exactly true, but in practicality, we would model it like this, where that resistance is just the sort of the bulk resistance of the semiconductor. So even when the diode is reverse biased, how do we know it's reverse biased? Because its cathode is closer to the positive side of the battery, so it's reverse biased. Okay, this current here is ideally going to be 0, and if that current is ideally 0, then we have 0 volts across here, and then all the battery voltage by Kirchhoff's voltage law appears across the diode. Practically though, this current isn't exactly 0 because the doping of the semiconductor, there's resistance there, so there is some leakage current that will move around. This is a little hard to do with the mouse. Leakage current that will flow through the diode just due to its inherent resistance. Okay, so when the diode, even when the diode's reverse biased, we generally will assume the current is 0. It never is 0. There's always small amounts of leakage current. And we'll be coming back to that over and over and over and over again as we go through the course. But for today, you can just simply assume that an open diode, the current is 0. Okay, if it's reverse bias, it acts like an open circuit. Okay. I would also encourage you to look at my lab video for experiment number 1. There's circuits very similar to this about diode biasing, potentiometers, and things. There is some review information in Canvas from first semester on potentiometers and rheostats. If you need a little bit of a refresher, you can check that out. But you do look at my experiment 1 lab video, and I think you'll find that that covers a lot of the same material. And do so before you do experiment 1 part A, please. Okay. This is the diode characteristic curve. Okay, you're going to read all this. You're going to read all these wonderful notes I made. Okay, diode curve. This is the nominal 0.7 volts bare potential. Is it exactly 0.7? No, it varies a little bit from diode to diode and depends on temperature, but it's an average typical value of 0.7. And this says that as we increase the forward bare potential, so we're forward biasing the diode, the current is essentially 0. Okay, and there's a little bit of a knee here, but essentially like this. And then at about 0.7 volts, boom, the diode suddenly turns on, and we have lots of forward current. If we're going to go in the reverse direction, then we're going to be down here, basically no current until we start getting to the breakdown region. We don't want to be down here. This will destroy the diode. Okay, so we don't want to be down in this region at all. So this is the reverse bias, and this is the forward bias. So if you go back to here, this would be the forward bias. Oops, sorry about that. And then this would be the reverse bias. Okay, so that's kind of where those tie back to. Diode model. Okay, and ideal diode forward biased. Okay, 10 volt here, 0 volt here, 10 volt here because there's no voltage here. Practical diode, this is around 0.7. Okay, but ideally it's going to be 0. And if it's reverse biased, okay, note where that is. Note this. Okay, for forward bias, note it's the anode. Okay, note that's the positive, right? Then if it's reverse bias, this is going to be an ideal open switch. So there's no current, no voltage. Everything then is developed across there. For the forward bias diode, okay, oops. Yeah, I just totally messed that up, didn't I? Yeah, okay. Oh well, get an eraser. Okay. It's going to be just like that, like a closed switch. Okay, practical diode. I mentioned this a little bit earlier. When it's reverse biased. Okay, this is the internal bulk resistance of the semiconductor. Okay, it's a rather large resistance, so notice that in this case we have 15 volts here, about 0.1 there due to the leakage current. Okay, so you have about 14.99 here instead of 15, so it's very close to being ideal. Over here, the resistance of the semiconductor appears sort of in series with the diode. So again, we have 10 volts here. We have 0.7 there, and that 0.7 is dropped internally across the semiconductor barrier potential, and that leads us about 9.3 volts for the load. Okay, diode testing. I think this is the last page. You'll be doing this in the lab, and again, refer to experiment 1 lab video and lab handout, please. On your multimeter, you can't sort of see this too clear, but there's a diode symbol here. Okay, it's a diode test function. Okay, turn it to there. Your meter will look differently, but it's still going to have that function. You may have to hit select or feature or something to show it on the screen, but anyway, you'll figure it out. And if the diode is good for forward biased, okay, it puts a little current through the diode. Okay, it should be 0.7 volts thereabouts. Notice that the red lead goes to the anode. and the black lead goes to the cathode. So this is the diode symbol. This is physically what it looks like. Okay, it's a typical black thing with a silver gray band on one end. If it's reverse biased, you reverse the connections. Depending on your meter, this is going to be 1 or OL. OL does not mean out of overload. It's a pet peeve of mine. It means out of range. It means that the resistance of the diode is so high, it's beyond the capacity of the meter to measure it. Okay, so this is how you're going to test a diode, and that'll be part of experiment 1. So I guess that's about it. So take a look through this, and after you've looked at the basic semiconductor theory, I would not recommend changing the order. Just wouldn't make sense. And then I guess in our next lesson, we should be in class, and we'll be looking at diode rectifiers. I do have a video on that. I would strongly encourage you to watch that video before coming to class. You can just get more out of it. And then after that, we're looking at Zener diodes, and then transistor biasing, and on into the course that we go. So anyway, hope this was enjoyable, and see you again soon. Yeah, cheers, bye.